All right. So we are live again for Shenzhen I. um, we have we still have the solitaire game that we have to open. So I think before people get in here, let's start with that. I think it is actually a task. We're supposed to enjoy a game of solitaire that the CEO's daughter made. So we'll try that as a warm up while everyone gets in here. Um, I'm not sure what I'm looking at yet. So does this work like? So we have three different suits. And I suppose you can stack any number on any number. I'm not sure what these symbols are. We have a 1 here, so that's not an ace. Maybe this is the bottom of the deck. I'll try stacking 9 here. Doesn't work. I'm not sure if that's because of color, though. Let's try stacking these on each other. Nope. Okay. And can we move whole stacks? We have another 9. Let's try to stack this on something else. Nope. I think I might already be stuck. Well, oh, hold on. We stack these in reverse, so we can start putting 2s up there. So what's our goal? We want to get to that 2. Let's unblock this by putting that up there, and it goes up automatically. Alrighty. Then we have another 9 somewhere. Okay, you can't stack them if they're the same suit. I see. Well, what's our next goal? We have a 3 here. Oh, so we could just put this 2 down. Where's the red one? Right here. Tyler, hey, welcome. You love this game? Worthwhile for anyone to play? Yeah, absolutely. I've been trying to get my younger brothers to play this game. I think everyone needs a little programming type game just for the exposure. It's good for your brain. Have you played much of Zachtronics? Okay, our goal is a 3. You know, I'm just gonna take one of my slots so I could put a 3 up there. It doesn't go up there. Oh, okay. Oh, I suppose the 1s go up there automatically. I have 1 here. I think I might have already worked myself into a corner. Well, we can put up the 2 and the 3 if we put this up there, right? So, yeah, 1, 2, and there's a 3 here. So we could put this up. Where's the green one? Down there. We have to move out to 9 and 8 for that. This is my first time actually playing a Zachtronics solitaire game. I played TIS 100, but it didn't have one. I don't need to put this green up yet just to get to that 3. I think a bigger priority is unblocking towards that 1. Or clearing out one of these stacks. If I could do that. You know, if I move this up, I could at least move the 2 here. And I can't move that 3 there, can I? No. This is not... Man, I'm gonna have to learn the order for these things. Can that stack on there? No. Can that stack on there? Can any of these stack on each other? Okay, I tried all of them. Nope, I have no clue what to do. Those, I'll call them face cards. I don't mind getting stuck on this puzzle because this is where you're supposed to go if you get stuck on the actual puzzles, right? And what is this spot here? Oh, these three symbols correspond to these three cards here. Why do we have multiple of these? I don't know what's going on. Did they just all go up there? Yeah, I have no idea what the slot is. Oh, instructions. We do have instructions. I thought all we had was the email. Okay. RTFM. To win, stack the 3 suits from 1 to 9 in the top right corner of the table. Okay, yeah. Cards being stacked and moved in the center of the table, but only if they are alternating suits and decreasing values, okay? The free cells in the top left corner of the table can store 1 card of any type. When all 4 dragons of a single type are exposed, they can be permanently moved to open a free cell. Oh, okay, those are dragons. By pushing the corresponding button. Aha, I see. Oh, Factoria is a great one, yeah. Fun story. My younger brother, and he was I guess he was a teenager at the time. He's really into Minecraft. And I sent him little challenges of things to do with redstone. So I'd send him like, do this, and he'd send me pictures of what he'd done. And what I was secretly doing, or not so secretly, was getting him to build a binary adder. And we made it all the way through. So yeah, I like that kind of stuff for kids. Factorio Minecraft. It's 10 p.m. here, so you're gonna go to bed? Fair enough, fair enough. Alright, have a good night. Hey, Zuno, welcome, welcome. Okay, so I think now that I know the instructions, I should start a new game. Oh, okay, we get 1, 2 off the bat. Already we can move some of these numbers into stacks. 3, 4, 5. I hope I'm not being too greedy here. They didn't mention any kind of stack limit. And this dragon's all the way up there, so that's gonna be hard to get rid of. But the square, the black dragons, are pretty shallow. We could get there. Yes, the instructions. I thought for a sec that was just email, and I was remembering the daughter's attitude that it didn't need an undo button because you just need to get good. So I thought, oh, okay, we're just gonna do this without instructions. Here we go. Okay, we can move this 8 over. And will we be able to, so we'll be able to move this 4 to here. We could put this red dragon into a free cell. Then we can get rid of the black dragons, right? Yeah, I think that works as a plan. I don't really want to put a dragon in the free cell if I'm not going to be freeing it soon, though. But that's the only thing I can really do with this, isn't it? Because I'm not going to get the green dragon cleared before the black dragon, so it has to go in a free cell. Well, it doesn't have to go right now, but it's too late. Okay, 1, 2, 3. Great. So this dragon does have to go in a free cell until I clear it. This 4 can move out there. Dragon free cell, and we get rid of the black ones. Sweet. Oh, we lose a slot. Can anything go in these? Oh, we can move that back down. So there's that. But what do we want to free up? So we still don't have the red one. I suppose we could always do red last. There's the green 2. All the way up there. Jeez, that's gonna be a pain. Alright. I think we just build stacks. So 6, we have 7s around somewhere. There's one here. That one's also kind of deep. Those are both deep. Okay, let's move the 9-8 here. 7, 8, 9. Cool. This 2 is not going to go until we get rid of that red 1 and all the red dragons. Yeesh, this game is tricky. Okay, do you have a 9 we can move this on to? Oh, no, we can't stack those. We really need to get rid of the green dragons. But I can't move this 2. Can we unblock a 3? Oh, yes, there's a 3 right here. Great, green dragons out of the way. Perfect. What goes... okay, this can go here. This will need to go into a slot like that if I'm going to clear it. So if we can find a place for this 4, we can move this 4 here, so that this alternates on the black 5. Okay. And the black 5 or red 5 can go on top of that 6. Which one do we really want to clear out more? I think we want to clear out that black 3. So we'll do that. Oh, there's a special rose card. Or not a rose. I'm not sure what flower that is. Okay, well, we're almost cleared with the 7s. Great. And we can move this here. And we've almost got all the red dragons out. We do have all the red dragons out. There we go. Excellent. Hey, this isn't so bad. Alright, we can start making our piles to 9. What do we need to unblock? Just the 3s. So let's do that. We still want to unblock the green 2, which is here. So let's just move all of those over. Hey, there we go. And we've got it. All right. Hey, not bad. Not bad. We get an achievement for that. Okay. Well then, shall we get into building circuits? I wonder if that email thread... Oh my god. They're... Oh, can I copy paste that? I want to read what they're saying. Here, I'm gonna screenshot that. And how do we do this? All right, so I put the screenshot in the ChatGPT. From Joe. Amazing. I just can't stop playing. Your daughter is absolutely incredible. Boss, please tell your daughter how good her game is. It's so good that I've completely taken over her father's computer, so you can't get any work done. That's it. The rest of the visible English text. Okay, yeah. That's cute. Cool. All right then. Before I start, so I did reopen Shenzhen I. Shenzhen. It's not pronounced Shenzhen. It's like I can't remember. I'll have to look up the pronunciations. But I did open up the game a bit, and looked at the ones I'd already solved and did some optimizations here and there. And as I did, I learned some pretty neat, important things. So just to do a refresher of our memory, I'm going to go review those and share what I learned. So here, the animated esports sign, this was the one I was most disappointed or like dissatisfied in. Right, so we've got these blinking patterns that we need to, oh, there we go. Yeah, we've got 3 different patterns of ones and zeros here, of on and off the blinker. So notably, like one thing I noticed here, these two, they're a group, right? One's only ever on when the other's off, right? So you could get one from the other just by doing a not. And then these last 3, they are also only one's ever on. So if you made the pattern for 2 of them, you could just do like a not or to get the 3rd one. So that's the first thing I tried to do. If you do it just with plain signals like this, you have to use a minimum of 3 chips because you need 5 basic output pins, and you only get 2 per chip. So I tried that. So here, I was able to drop down to just 2 chips. Here's a not or, and here I use a straight up not to combine those simple signals. And it's simpler. It's simpler. But I did more than that. So after that, I learned about this chip here. So what this chip does, it takes it can take an X input, and the X input is something like 101 or 110, whatever, and it lights up these 3 based on that pattern. So instead, I can just hard code those patterns. So I have 001 for 6 seconds, and that corresponds to, in a simulation tab here, this 6 seconds of drink 0 being up, being on. And then I switch states 010, and then 100, etc. And then this gets me what I'm pretty sure is like the minimum power, because it's the minimum number of instructions running. You run an instruction, you sleep as long as possible. You run an instruction, you sleep as long as possible. And there's only like 2 groups of those instructions. So that was nice to learn about this chip. I also found other handy uses for this chip. You can always use it for turning an X1, an X output, an X bus into a normal basic output. Yeah, that's not min production cost, but it is min power usage. And then I went for min cost here, and I don't think it's the absolute minimum. You can see here on the graph, really tiny sliver, someone's done it in 6 yuan, but they're a very small minority, so I think that's probably pretty hard to do. But let's see what I did. Right, this is just the same pattern. I just took out the not, and I used both output pins of this one to drop another unit. And then I decided to try and go for min lines of code? Because I see here some people have done it in like, is that no lines of code? So I looked through the manual and I found this. So here's read-only memory, and here I can hard code all of those patterns. So this is a pattern for the drinking lights, right? So 111, those first 6 ones are just the drink 0 being on, etc. And then after that, after 10 steps, I jump back on the loop. The right side again is still this DX300. And then I do something really sneaky here. I keep the click outputs in the accumulator, and just on every clock tick, I knot that, and then I move it out. And then here I've got another knot, because these two are always opposites. So this is what I could get for minimum lines of code. And yeah, pretty happy with that. Oh, I guess I was able to get even fewer lines of code. No, I just have an alternative. Oh, right. Yeah, I can do this with a smaller chip. I think that's part of the goal. Yeah, make it cheaper. Yeah, I was hoping to minimize as much as possible by using 2 of these. And then I could use the X version of this chip, which just has all X outputs, and use this to convert that to a P instead of using the P output to do that. Yeah, that at least was able to drop me down from using the $5 chip and use a $3 chip instead because of the pin configuration. So I learned a lot just by looking at that, plus I'm trying to optimize a bit. Drinking game counter, that wasn't too interesting. The rubbish audio thing. Okay, so here, my original design, I had all my logic in one chip. I use a second chip to convert an X to P1. And here's where that DX300 comes into play. I can convert this. Oh, I was saying you can convert an X into a P. You can also convert a P into an X. So now I can just act on the X input, and now we have 2 inputs and 1 output. Which means we only need to use 1 chip, and this DX300 is only a $1 chip, so that cuts costs by 2 yuan, as well as power and lines of code. So a good little trick to have in your back pocket. The infrared sensor. What was my issue? So this was a similar issue here. I have this $5 chip. I'm not using most of the space here. Well, actually, no. The issue here was bigger because we have 2 P inputs, right? 2 basic inputs, and then we have 2 X inputs as well. So here I was able to like dump it all into 1 chip, one of the big chips, and then I use this chip to convert that. So that's another one where I can use the DX300. But before I got that solution, I tried this. So I tried to get rid of the big chip and use this 2 of the smaller chips to cut. I'm not sure why exactly. I think I was trying to cut the cost, right? Because this here is a $5 chip. So 5 plus 3 makes it 8, right? So I was able to drop that down to a smaller chip. And this is where I first started using a pattern of like blocking. So here, I have the time input split across 2 chips, right? So I set the on time here, then I send the on time to this chip. And then since this chip has the other, the off time, it can do the calculation to see like whether the chip is live or not, whether it's armed, where the sensor is armed. and then it sends that back here. So this blocks and waits back and forth, completes calculation on another chip, sends the result back. And then from there, or I think it just used the result here. Right, and then this chip can use the sensor input to get out there. So it's still useful to learn that kind of thing. But ultimately, the best approach was just to use that $5 chip, and then because it can handle all the inputs, and then just convert it with a DX300 here at the end. And that's the best power, lines of code, and cost. I think someone's using slightly less power, but yeah, pretty minimal, pretty optimal. So I like that. And last but not least, the virtual reality buzzer. Yeah, so this one's pretty simple conceptually, but it has some trickiness here. So this RX radio input, it's a non-blocking X bus. So when there's no input, it just does -999, right? And the issue here is that I have to use this big chip because it has two registers, right? The accumulator and the data register. And the reason I need two registers is because you can only read this once. You can only act on it once. And then there are like three possible states, right? So it's either on, off, or -999. So you have to save it to the accumulator and then act on the value in the accumulator. And then the data is what actually tracks my state, whether we're supposed to be buzzing or not, or rather, like whether we're buzzing or not. And then of course there's a whole pulse thing here. We don't need to talk about that too much. So I tried to get around using two registers, right? So I tried to sneak it down to just one register, the smaller chip with just one register. And my first approach to do that, oh, okay, this is a little hacky. So I think this is one I might actually need to step through. But what I do is I move the radio input into the accumulator, right? And then let's see, if it is nothing, then we keep moving. Wait a second, that's equals 0, right? So if it's non-zero, then we move the accumulator into X1 here. And I'm using this DX300 basically as a register. Yeah, so the value in the case where it's on is 100, right? So that turns on this pin. So we can simulate that here. So -999, and eventually, okay, eventually we get a 1. Oh, 001. Okay, so that's gonna turn on this bottom output of the DX300. There we go. And then now, in that case, in my main loop here, what I'm looking at is this this input pin P0. And I check if it's 100, which is to say that the bottom one is on. And that's the case where we are armed and we're supposed to be doing our toggling or our pulsing of the vibrator, right? But here's the thing, that stays on the whole time, right? So this is kind of like a flip-flop. So it still stays armed even as we go back through the top of the loop. You know, even once we get -999 or whatever, that keeps happening. And then at some point we get the 0. Let's see, we're almost there. Yeah, and as long as that's on, we do our pulse, our little vibration, right? And at some point, this this thing is going to be off, and we'll get to how we turn that off here. So now we have a 0, and in this case, whoops. Oh, I advanced too much. Oh, okay. Here, let me just advance straight to that. Okay, so here we have a 0 coming in. Okay, so since it's not equal, hold up. All right, yes, since it's not negative 999, we move the accumulator to 1, right? So the accumulator is what had our radio. And when we move that accumulator to x1, that 0 turns this off. So we're only moving 1s and 0s into this DX300 whenever the input is not 999. And that turns it off. And since we only ever pull in the input when it's not negative 999, then that stays off until we get another 1. So that was really satisfying to do. Yeah, using the state of the DX300 as a spare register. And then I did one more thing with that. Oh, yeah, so I did another one. It's simpler in concept, but it also has some trickiness. And the trickiness here is to basically overload accumulator and have it have multiple meetings. So now we actually test if it's equal to negative 998, because what I do is I add the value into the accumulator. So I'm looking at multiple possible values of the accumulator there. I suppose there's no need to step through all of that. But I found a way to do it with just one chip, just one register, in fact. So we keep testing if it's, yeah. So instead of testing for like any on, what happens is we add the x0. So if we add 1, it becomes negative 998, and that negative 998 now means that we're on, and 0 has no effect, right? So that it will stay down on negative 999. So if we step through here, yep, now it's negative 998, and then we add back 999 to normalize. And then we fire our little pulse. And then now, so the reason we added that negative 999 is because at some point we're going to, that 999 is because we're going to get to negative 999, and that'll drop us back to negative 998, which tells us that we're on. So we are constantly adding and subtracting that same value. And then eventually we hit 0. And in this case, we added 0 there. What happens? So we add the 0 to the accumulator. Right, since we didn't add the negative 999, then this isn't on because it's not negative 998. Yeah. So that was really satisfying. It's a hack that I hopefully won't have to do, but it was fun to optimize. Anyway, the whole point of all that being, I've learned some tricks that might come in handy if we get there. Okay, so let's do a new puzzle. So prototyping new ideas. Sometimes a decent puzzle idea falls out when you're faffing about with chips and code and the like. Oh, yeah, this guy's from the UK, right? So I've set up an empty prototype board for us to experiment on. Okay, on you go then. Chips. We can test with some different parts too, such as custom LCD panels. I will add other parts as we receive them. Okay. Custom LCDs, are you serious? That's brilliant. We could make retro-style handheld games. Let's all take turns designing one. Is this one open-ended? Carl, come see me. If you have finished all your other assignments, I have more work for you. Who's this Carl fellow you mentioned? Nobody we know. Objective, design and create an electronic game. You have to click and hold this button to indicate that we've completed. Oh, this is an honor system. Oh. Well. Oh, wow. Okay. I don't think I'm ready for something that open-ended yet, but oh, look at all these parts. This is fun. I'm pretty sure none of this is in the manual. Let's see. So we have an LX100W is one of them. Oh, let's start from the top here. I'm just gonna scroll this up. So all the new things we haven't seen before. An MC4010. We write a command sequence to any pin to instruct it to perform a calculation. Command sequence consists of an operation code followed by one or two values. It's complete. A command sequence is written to MC40. Result register is updated. Okay, so it takes input. This part is for prototyping only. Okay, so it's a smarter chip. This is probably where that guy made the Minesweeper, yeah. I might have to start with something simple like tic-tac-toe. But I won't do it yet. I just want to see what new toys we have. So the N4PB1000. Well, we have the 8000. Where's the 1000? Push button controller. Okay. N4SW. Where is that? I don't see it in here. Well, yeah, the N4DL. Nope, I don't think that's in the manual either. This is fun. So just a lot of undocumented parts, and we get to figure out how to use them and what to do with them. The LX1000R seems to be some sort of light. And then we have LCD displays, which are also, no, is this one of them? LX910. Oh yeah, here. A 7-segment display. And this is a touch screen controller. Crazy. So we can click around on there. Wow, okay. There's a lot of, you can get actually pretty sophisticated with this. Okay, well, I'll take some time to look at that later. And we can have our fun. I just want to see what some of these parts look like. I don't remember seeing that in the manual. Wild. Oh, I recognize this. This was from the clock puzzle. I have no idea what that is. Okay. A lot of crazy stuff to learn about. Oh, and where's that? So this is a touch input. That's what that is. And the other one's segment display. To add a custom screen to Sandbox, create a grayscale image that's exactly 320 by 405 pixels using black for segments. Save as a ping. Oh. Oh, we have to actually put an image in the game files and restart the game. Okay. I think I'll save like a whole night from making a game in Shenzhen. Because that looks pretty fun. Okay. That'll be fun to play around with. A little help. Product, a wireless game controller. I'm wrapping up a project to make a game control console and could use some assistance. Before you get too excited, it sounds far more fun than it actually is. The console is just a tiny, super cheap box we're making for Sleep Cubes, the big Japanese capsule hotel chain, to stick in every pod. The games will just be some free dross they find, I'm sure. At any rate, I've got it mostly done. I just need a module for the little wireless controller that comes with it. I ping you, you tell me what's going on. Nothing much more than that. Okay. All right. So X and Y simple inputs are connected to a joystick. Okay. A and B are buttons. Okay, so we have 4 inputs. Radio RX is a non-blocking X bus connected to a radio receiver. Radio TX is an X bus connected to... Oh, I could have used TX the whole time? No, I'm pretty sure that one that had this chip before was only using RX. Like the other one had been disabled altogether. Okay, and what are we supposed to do? We have an X and Y. So we tell them with a TX. Oh no, TX is for transmit. So that is our... No. When a data packet is received over the radio from the game console, respond with the following 3 value data packet. Okay, so data packet is received. So I guess RX, here's a non-blocking input, and then we go output to TX depending on the current state. I see. So radio RX is our input, and this is the expected output of 3 values. Okay. So three value data packet. So 0 if A is 0 and B is 0. 1 if A is on and B is off. 2 if just B is on. So we're supposed to give... I'm not sure actually what it's... What do you mean 3 value output? So in this case here, 63, 37, 0. Oh, so we send the X value, the Y value, and then the button state. Okay. X value, Y value, and button state. I think... Oh, I was gonna say we could just use the logic gates for the A and B values. But let's use chips. So we have 4 inputs, 4 basic inputs, so we need at least 2 chips. Why don't we start with that? And I suppose we have to send those in turn. 3 data packet, or 3 value data packet. Okay, so first send X value, then Y value. Let's do it this way. P0, P1, and that's going to go out with those 2 values. And then after reading both those values, we'll read the state here. We'll do a similar wire setup here. So B goes to P1, A goes to P0, and we'll have an output here. And I suppose they need to be coordinated, don't they? So that's possibly a third chip, or we send values to another chip. I think this chip on the right will have more logic on it. So what we could do is send this result to the first chip, which then, oh, yeah, we could send it to the first chip and have this chip send it to the output. Oh, this isn't like premature optimization. I just don't want to do a third chip. Okay. Yeah, so send P0, send P1, send X1, all in turn. But only in response to getting a -1 input. Oh boy. Is this one of those cases where we're going to need to... Oh, there's only one possible value that this can have. So I think we can use the accumulator for this. Let's just move this over here. Hold up. It also needs to receive input. And we can't like have those connected to each other. Well, we are getting to premature optimization territory, but the other side I have is like, hey, this here has an X output, like we could use that. Right, so we could send everything over to this chip instead. But the code might be tricky for that, so let's keep this simple first. And then we can optimize later. In fact, oh, they don't recommend the MC4000X. Now I'll just do a third chip. Okay, so this needs... Oh, well, in this case, both of the X chips are used. Right, and this needs an X out. I'm going to use this part that's not recommended. Or, you know, we could use a bigger chip. Let's use a bigger chip. All right, where should the bigger chip go? I suppose we can put it on the right here. Because if we do that, then there's also more space for the logic here, and this will need more logic anyway. Let me also refactor this down here. There we go, I like that better. All right, something needs to be connected to both of those, and it's gonna be this chip on the right. So what we could do, oh, hold up. This thing needs to move because we need to get to the right side. If we use a bridge, we can expose one of these, but not both. So we could put it here. We could put it here. I think that's what I'll do. And this can flip around. We could just connect that directly like so. I want to see the pin names. Okay, this is X1, this is P. Oh, wait. This actually has to go up higher. Okay, we don't need this chip. And this can actually just connect all the way over here. Okay, so we have a circuit. The X and Y will go in on the left side, and they'll be passed over to the big chip. The big chip will read the A and B values. Well, it'll read from the transmitter, and then it'll pass along the X and Y values. And then, oh, this has to be synchronized. It wants the X and Y values at those times. So it reads from the transmitter, sends a signal to the small chip to ask for the X and Y values. So you start by moving the input. It's RX. Yeah, receive, which is X0. So we move X0 to ACK. Okay, and if it's -999, we think we can just ignore it completely, right? I think I want to have this be like a plus and jump up. Wait, do we have jump commands? I forget my instruction set because I've been playing the other game. So we have program structure. Yeah, there's a jump. We only have one jump command. Right, we don't have a jump equal or anything. Okay. So that's how we'll do it. While that thing is -999, we just keep reading more input. So plus jump to start. And we'll label this as start. Is that how labels work here? It should be on its own line. There we go. All right. Otherwise, we start reading all the values. Right. We want to read it alive, so we do still have to send a signal to the left one, right? Otherwise, if it'll like read what it was like so and so time ago. So we're gonna move just 0. Do we have nil? let me look at arithmetic. I don't think we have nil. I like it semantically, but it is just 0. So move 0 to the small controller, which is x3. Oh, wait, right. There's only move ac, so move only has one argument. That's why I was confusing myself. So we move ac to x3. And then here, it doesn't matter what it is. So we can just move x0 to ac. Move does take 2 arguments. So we move ac to x3. And here we move x0 to ac. Can we just move it to nil? Can we just dump a value out completely? So we actually don't need the value of that. Okay, so once we get that signal, then we move p0 to x0 to output the x value. Jeez, okay. And we move p1 to x0. And then we wait again for the next signal. Okay, now here on this end in the big controller, we have both of those inputs. They're both coming on x3, so now we move x3 to x1 to transmit, and then we move x3 to x1 again. Okay, now we need to do logic for the controller. So let's look at our information. If A and B, so 0, 1, 2, 3, this is basically, this is binary, right? Let's see. So if A, we have 1, if B, we have 2. And if both, we just add 1 and 2 for the 3. Okay, what value comes in? We get -1 come in. So I'm going to move 0 to my ac, move 0 to accumulator, and, or I guess data value. Move 0 to data. Because we need to do a conditional on this. It'd be nice if I can just convert 100 to 1 and 100 to 2. Well, we'd still have to do that with the accumulator register. Okay. So we move P0, the A button, to the accumulator. And if that is on, we add 1 to the accumulator, to data. Oh, hold up. We have to swap values between. Move P0 to the accumulator. We still need to run a test. Okay, so let's test. So, test, if you have a test not equal to 0, oh, sorry, I've been blocking this the whole time. Oh no. Right, so recap what I was doing here. This chip waits for input, moves P0 out, moves P1 out. Pretty straightforward. This chip, we move, we wait for input from, we keep pulling input from the RX, and if it's not actually input, then we jump back to the start. Oh, this jump, we don't actually have a conditional here. So we test if it's equal to -999, and in that case, we jump back to the start because we're waiting for an actual input. Test equal accumulator to -999. And I suppose that doesn't need to be in the accumulator, right? That could be in the data register. What are my test instructions? There we go. And if so, we keep jumping back to start. Okay. And then this is the easy part. We pass on our signal to X3 to a small controller, and then pass the signals from the controller out as our first two parts of our data packet. Great, so now this is the part where we do the logic for the controller. So we're moving P0. Well, yeah, 0 to data. I was moving that because I'll want to like add. I suppose I don't need to do that just yet. Let's move it to the accumulator because we're going to be adding things to it. So what we can do is move P0 to the data register. And our test instructions can work on the data register. I'm still in TIS 100 mode where all of your comparisons happen on the accumulator by default. So there's no like two arguments being passed to it. So we move P0 to data, or we can just compare P0. So if P0 is on, then we add one, our A button, right? And then if P1 is on, we add 2. And now our accumulator has the value we want. So we move accumulator to our output X1. And we just need a plus sign here. Okay, I think that should do it. I'm pretty sure that'll work first try. I love saying that. Okay, so what's actually going on here? We are following this loop. I suppose we're never consuming the -99. Oh, right, we have to sleep. I suppose before we jump back to the start, we should sleep. I don't want to sleep before we do everything else, though. And I don't want to start with a sleep. It probably doesn't hurt. Let's see if that works. R is not blocking. Oh, right. This needs to sleep too. Okay, so what's going on here? Oh, right. We just haven't run it through. Part not sleeping, blocked on read. That's not good. Oh, we should be in a sleep loop continuously until we actually get a read. Don't. Well, we're okay with blocking on read, right? I guess we're not. So I suppose maybe we need to duplicate this logic here. This test that's not -999. So the first thing the right one does is sleep, and this one over here is not sleeping. Why can't the right one move along anyway? Move X0 to back. Because this has infinite stuff to simulate, I suppose. Let's just put sleep at the start. Okay. So that is blocking on the input while we do other stuff. Hey, that looks good. But now what happens when we have all the negative 999s? Right. Yeah. This stays blocked on input while the other one is in a sleep loop. So they both need to be in a sleep loop. So we need to have a start here. And what do we actually want to happen on this chip? So we start by moving the X0 to the accumulator. It's going to be the same value that was transmitted. And then we do the specifical accumulator to negative 999. And in that case, we jump back to start. And I'm going to start with a sleep. So the system comes online, it starts by sleeping for 1 second. Hopefully we're not missing anything, right? But now, here we must always send. So previously we were only moving ACT to X3 in this branch of the loop. So I'm going to delete that line. So move ACT to X3. Part not sleeping, we are blocked on right. Why? Because one's sleeping while the other isn't. Okay, so we pass along the signal. Oh, hey, these aren't doing the same thing. That's why we need negative 999. All right. There we go. Okay, so it turns out, hey, good. So production cost, a lot of people did 8. Some people did it in 6. Yeah, you should be able to do this with just 2 chips. That does feel daunting though, because, well, this logic here was actually less than I thought it'd be. So this is for handling the controller. That's not bad. A bunch of this logic is duplicated. If we put that down just on one, well, I tried to put it just down on just one chip. We do move X3 into X1. We could have like a conditional kind of a thing where so we could move this to the smaller chip, and then the smaller chip can either send back like, hey, this is a no-go, or send the first input. If it sends the no-go, then we do the no-go over here. Otherwise, we expect another input. We would still have the problem, though, of where to place all of these inputs. Right, if we had... no, that just straight up doesn't work with the MC4000 chips. We'd have 2 fewer of the X2. No, I guess the chip layout does work. Right, yeah. We did talk about that, but that's a lot of logic. Okay, so I'll revisit that. I think at the very least, maybe a DX3000. We don't have to worry about making that sleep. So there is that. I'll just take a quick look at doing it that way. You know what? Let's duplicate the first one. Okay, so if we get rid of this, let's do a DX300. That's only a $1 chip. That's probably the cheapest way to make this just 6. And where's there room enough? We could do this way. And okay, so we have next output based on this. And I suppose we can just read this whenever we want. So in this case, well, no, that's not going to work. That's not going to work. These aren't just on and off. These are scalar values that need to be sent all the way across. The A and B, on the other hand, the A and B could be handled that way. So let's say big chip is here. Let's flip this around. We could do this that way, I suppose. Okay. So we just kind of convert that into binary. I think P01, P1, P0, P1, P2. Let me just check DX300. P0 is the first digit. No. If the X value is 100, then P2 is on. So P2 is the biggest digit. Right, so here we're going to get just the right 2 digits. Okay. Now on this end, P1 and P0 need to be connected to X and Y. We could use a bridge here. Oops. And that we just connect all the way. Let me rewire this a little bit here. There we go. That's a little bit cleaner. Okay, so the A and B P's get turned into a single X. Great, and now these other two x's. Oh boy, we need another bridge. Nope, no, we just need to move the whole thing to the left a bit. Or to the right. How much space do we need? Yeah, that much space should be good. No. There we go. We can flip this transmitter, radio chip around. Okay, so that's connected. And now this Y chip can connect to P1. All right, that's all wired. Now we just need to change the logic. I hope. So when we are reading from an X bus, it captures a state. Every time we read, the digits of the resulting X bus value will be set to either 1 or 0 depending on whether the pins are off. When representing a state of simple I/O pins, the value of the ones column corresponds to P0, while the tens column corresponds to P1. Yes. Was I blocking that? Okay. Here's the design. It's cleaned up. I need to be better about not blocking what I'm doing here with the manual. Okay, so from here we just need to change our logic. So we have our sleep loop. We're no longer using X3 in the same way, so you don't need to pass along the radio value to the X300. We still need to move X0 to ACK. We still need to test on that and then jump if it is -999 back to the start. Okay, so now let's move X3 to X1. That was supposed to be a joystick value. So now we can just move P0 to X1, and here we can just move P1 to X1. And then now we're capturing our state. Now, basically, the binary will be correct. Too bad we can't just convert. Right, if A is on, this is the ones column, right? And we do kind of a switch case, right? If 11 send 3. We have a digit selector. Command. Oh, yep, here we go. Oh, where was that? Arithmetic instructions. So digit, isolate the specified digit and store the result in the ACK register. Oh, that overwrites. I don't like that. Isolate the specified digit of the value in the ACK register. Okay, so digit command is basically a mask. And And we're not testing on P0 and P1 anymore. We've got the value coming from X3. Well, I suppose we can move X3 to data. And we could do test equal. We don't have enough space for to check all of them, right? Test equal 11, etc. We do need something that's more direct. Yeah, okay, we're back to we just really can't fit all that logic into even one big chip. Even with this, I mean, we could move X3 to data, get the digit, move X3 to data again, get the other digit. Or X3 to accumulator. But then we have to swap between accumulator because we need to use the accumulator to add. All right, well, the only way to salvage this then is with the small chip. And if we do the small chip, this needs to sleep, which means we need to pass along the RX over to this chip. We're back to our first design. Well, that's unfortunate. All right, we can come back to that later. It wasn't bad. I suppose I could make it smaller at the very least. I'm wrapping up the project to make a game. Oh, yeah. Thanks, mate. I owe you one. You just helped me make thousands of dead tired salarymen marginally happier. That is, if they actually find a console and use it to play a game before passing out. Cool. Feel the connection. Get ahead. Are you lonely? Do you feel isolated and disconnected from the world? Scientists have shown that the lack of real-life ties to others can lead to to depression, which in turn can negatively affect performance at work. Don't let the lack of human interaction reduce your effectiveness. Virtual friends from BuddyBots are quality friends nearly indistinguishable from real-life people. Okay, so you get an AI friend if you're lonely. Our characters are developed by the world's top personality designers and are completely customizable. This came out before ChatGPT, right? So whether you want a supportive presence to help you get through a difficult time or a flirtatious sidekick to banter with throughout the day, you're covered. Subscriptions are flexible. Okay. Oh, stop being lonely, feel the connection, and become a top contributor of your company's success. I like how the point of this is to become more productive at work. Agurite, laser tag equipment. Create a working design. Okay, yeah. Please don't blame me for this. I have a friend, more like an acquaintance, really, from a while back, many jobs ago. He's always been a bit of a nutter. And I guess what happened was he made a decent bit of cash with an app or something and decided to retire from the programmer's life and build a laser tag arena for the rest of his days. Sounds kind of nice. That's not the worst of it. He's calling his franchise to be the Awesomeplex. Oh my god. In any case, he wanted to see if we could make some scorekeeping wearables for it. And I said yes. I'm not entirely sure why. I suppose in the unlikely event his arenas do take off, it'll look brilliant in hindsight. Awesomeplex! With 3 exclamation points. When it's done, we should try a match in the office. Laser tag looks so much fun. You know, this is kind of a fun idea. A lot of simple inputs, either on or off. Too many for a microcontroller on its own, but good use for DX300. Oh, okay. Well, we know the DX300. Okay, hit respawn alive. Trigger, reload, fire. Hit is a simple input. Respawn is a simple input. Alive is a simple output connected to an array of LED lights on a vest. Laser sensors, quick connect jacket. Great, trigger and dead are simple inputs connected to switches in a replica gun. Fire is a simple output connected to a laser. And an effects module is a replica gun. Wait, sorry, what? Fire is a simple output connected to a laser and effects module in a replica gun. Okay, so that's output. And when a player is hit, their vest should be set to not alive. Okay, so these are inputs. Alive is the output. So this is the main thing we're changing. Trigger is an input. Reload. Yeah, trigger and reload are inputs. And fire is an output. So I'm guessing we fire when the trigger's on, given that we are alive. Something like that. When a player is respawned, their vest should be set to alive. Okay. When a player reloads their gun, whether alive or not, their ammo count should be set to the ammo reload value, which I suppose is this. When a player is alive, pulls the trigger, and has ammo remaining, the gun should fire, and the ammo cut should be decremented by 1. Okay. And to allow for realistic operation of various replica guns, the ammo reload value is set by the operator using a dial that can be read as an XBus input. So this is XBus. Okay. Well, we have one XBus input. And how many simple inputs? Hit, respawn, trigger, and reload are simple inputs. DX300. We could turn that. I think it does make sense to group these. Maybe we can change our mind. So now we have 2 XBus inputs instead. And then we have 2 outputs. So we need a chip just for the outputs. I doubt this chip is big enough. It's not big enough on inputs alone, but certainly not for the code. Okay. So let's read this into X1. This is our hit and respawn. Well, let's take a step back real quick, because when a player reloads their gun, whether alive or not, okay, so reload can be like pretty independent, right? When a player is alive, pulls the trigger, and has ammo remaining, alive, trigger, basically alive and trigger. Wait, is alive an input? Alive is a simple output, but it is an input to a different function. Right, so we use the value alive multiple times. Okay. So when alive and pulls a trigger and has ammo remaining, you know, we could I want to code this out with multiple chips and make the logic really simple. Hi, Sparkly Dark Matter, welcome. So there's this triple and. This condition here, I could do it in two different ways. I could connect all three of these to a DX300. So they are alive. They're trying to reload. Oh, no. Reload doesn't go in there. When a player's alive and pulls the trigger, so here, alive, pulls the trigger, has ammo remaining. So we could make has ammo remaining its own input and plug it into there. But it's probably smarter just to have this two conditional. This should be an AND gate. When both of those things are true, then that arms the thing that will decrement that ammo count if possible. Oh, this isn't even keeping track of ammo, isn't it? This is read-only. So we have to store the ammo count elsewhere. Okay, yeah, there's a sub-register somewhere that's storing ammo count. And that register needs to be read for when the player pulls a trigger. When a player is alive and pulls a trigger and has ammo remaining, the gun should fire and ammo decremented. When a player reloads their gun, whether alive or not, their ammo count should be okay. So the main thing we're tracking then in all of this is really just ammo count, and then hit. To do our alive state. And fire if we can fire. Okay. We'll have this chip handle firing then. And it was trigger, alive, I just want to add and these. I know they want to use the DX300, but oh, do we not have AND gates here? Part not recommended. Maybe I shouldn't do that. but I want to. It'd make it easier to read, wouldn't it? I mean, otherwise we're just going to check if it's equal to 11, which is essentially checking and. Or, you know, we could read all the inputs into one bus. Okay. Except this P0 kind of counts as an input too. So this accumulator, the accumulator needs to be used for logic. This data can track alive. And this data here, or this accumulator, can track bullets. I think we need 2 big chips because we need more registers than that. Here's live impulsive trigger. Okay, let's do a big chip. Well, let's just start writing it here. If we need it, then we'll use it. So there's always a sleep. Decide whether to fire. So we need a live and pulse trigger. So we can have a DX300 that is connected to a live and trigger. And that's the only time trigger is used, right? Yeah. Let's set it here. Live impulse trigger. And now we've just converted that to an X input. Okay, so move X0 to ACK, and we test if ACK is equal to 101. And in that case, we can fire. Well, we also need the ammo count in here. Should I have to do this? Okay, this gives us the ammo count. Or like the max ammo. Oh no, we don't ever need that here. We just need that for the reload function whenever reload hits. I know they are encouraging us to use DX300s. I kind of want each of these inputs to be sent to its own small chip so that the logic can be, you know, all encapsulated there. Okay, so we need a data register because if we're moving things, we have to move things to ACK in order to compare them. So we don't actually have enough space here vertically for a bigger chip. Probably have an easier time if we don't spread out so much, I suppose. Okay, so P1 is an output for firing. We can put bridge here, and do that. Yeah, let's focus on the circuit first. So P1 is an output for firing. In order to fire, we need to know if alive. We already know if alive, so we can get rid of this bridge, because if alive will be tracked in here, yes? It's basically kind of a flip-flop on... I wonder if I could use that same trick from earlier where I used the DX300 basically as a register that tracks if we are alive or not. I think I would like to do something like that. I'm going to move this chip over to the right. Let's just get this out of the way for now. Okay, so if is alive, oh, I do want a DX300. So we send like a signal here. Hit is the only thing. Hit. Well, respawn will turn it on. So we could send a value to turn it on. And then we could send hit to turn it off. So hit's going to be a 100, so we could connect that directly to here. It's not an X bus though. I was thinking for a sec I could turn like 100 into here, and that will turn this on. But no. Okay, we still need... the ammo count here, so this is going to be our fire. We do have our alive state. We can't store them both in here. We need another chip for storing our alive state. So whether that's DX300 or something is going to store our alive state, and we're going to have to request it off of some other pin. And the other thing we need is trigger. Alive and trigger. Yeesh, this one is tricky to wrap your head around. Fire here to the bottom. Alive and trigger. Reload, and it just doesn't make sense to combine any of these. Hit and respawn kind of makes sense to combine. Yeah, okay, so this thing is going to be for handling fire, right? And I need another chip. We're gonna just leave that to the side because that's kind of stumping me for a sec. And I want to think instead about the alive system here. So when we are hit or when we respawn, when we're hit or respawn, controls whether we're alive, right? The player's alive. Oh, no. The players respawn, their vest should be set to alive. I don't know. I don't like using the DX300 here. I know Yi was saying that, but I just don't like it. It's like hard to think about. Right, because like let's say we do connect this. Here's why I'm saying that. What happens if this comes out like 11? We are being hit and respawning at the same time. I suppose that shouldn't be a thing. We can take priority over the respawn. Like read in the X bus every time we want to check one of those two values and just ignore the other value, basically. But why not just read P0 or P1, right? Okay. So data will keep track if we are alive or not. Let's read from X0. So move X0 to ACK. And all we want to check, so we're going to select a digit. We're just going to check for hits. And if there's a hit, we set alive to 0. So digit, how does this work? Set or read. So digit 0 here is the rightmost. Right. Wait, how does that correspond? So 210, same thing here. So digit 0 is going to be corresponding to P0. Okay. And now we check test of equal 001. This means we've been hit. So now we move 0 to data. We are dead. Sorry. Test of equal act to 001. Okay. And actually, part of the reason I put this here is because I kind of want to use this as an input too. Right, so now in this case, we can actually check here. We have been hit and we were alive. So that becomes 101. In that case, we say that we're dead. Right, so there's not a necessary step otherwise. Desu, welcome. Yeah, I'm liking that. And then now we again move X0 to ACK and we look at digit 1. And this is the respawn. Oh, hold on. This test equal, that doesn't work anyway because we had digit 0. So it's going to set that to 001. if we hit. So we move 0 to data, that's our alive or dead. And now we do a test of equal. Back is 0, 1, 0. So now we're being respawned. And if that's the case, we move 100 to data. Okay, that's not bad. And now we just move data out to P0. And we have an alive output. Okay, so that chip wasn't too bad to do. I need to sleep 1 at the end of that. So if we are hit and respawned within the same second, then we end up still alive. 100 to data, then move data to P0, our alive state. Okay. Well, now that we have an alive state, let's use that down here. So this thing's data register will keep track of our ammo. So every time we reload, again, we could use a DX input. And what are these values here? Oh, swap this around. Okay, so we have the P0 bit and we have the P1 bit. And we can just read those and respond appropriately. So we handle the easy one first, which is the reload. I don't know if we should start with a particular state. What does it say? When a player is respawned. Okay, so reloading works whether you're alive or not, right? What is the initial state, though? Let's just check the verification tab. That will tell us. No, that doesn't tell us. Because it's not an output. Well, we can infer it. So here, there's a trigger, but there was no fire. Okay, so it starts off empty. And then after a reload, the triggers actually do fire. Cool. So, oops. Oh, let's go back into there. So our data starting at 0 is perfectly fine. Let's move our X0 to accumulator. And let's get the 0 digit, the reload. So digit 0. And we test if that is 0, 0, 1. So if reload is on, then we move ammo amount here, P0, or we'll put that in X1. We move X1. You know what? Can we just move this down here? I like that better. And just connect that directly. Move X1 to data. Great. And then now we do the same thing again. We check the value. So moves X0 to back. And last time we're getting digit 1. That's equal act to 0, 1, 0. Okay, in this case, we are pulling the trigger. So now if we are alive, so let's move P0 to ACK. Move P0 to, that's the first condition, alive. And then let's do a test if our data, which is our amount of ammo, is greater than, no, we need to test greater than. Data needs to be greater than 0, right? Yeah. And if that's the case, then we are still fine. It's only when it's not the case. In fact, let's do it this way. Test equal data to 0. So if we're empty, then we're going to move 0 to a hack. Which is to say we're not going to fire. And then, basically based on act, so test equal act 100. So if we're on, then we're going to subtract from our data. I guess we have to move. I'm going to need more lines of code here to get that comment. So we move move data to ACK sub 1, and then move ACK to data. Okay, wow, that barely fit in that chip. So if the trigger is being pulled, then we do all this logic. Oh, hold up. Sheesh. That's not great. Oh, right here, we can handle it here. So test equal act 2. So if it is 1, we move 100 to act. Right? So we're firing. Or we move alive to act. So our conditional does get saved there. Okay, let's try that. Maybe a valid register date. There we go. And it's not sleeping. We have enough space to sleep. Oh no. Okay. We need to golf this just a little. Yep. So this whole bit here, we check if we're alive, and we check if we have bullets or rounds, ammo. And if not, we disable that functionality. Then we check, and then this found chest is if we are actually firing. Maybe I need to put a conditional on a test command to compress these a little bit. I haven't worked enough with this particular assembly to like have learned a lot of tricks for golfing. This stuff at the top, this is pretty much unavoidable, right? 1, 2, 3, 4. It just takes 4 instructions to do that. Move, digits, test. It'd be nice. This is kind of why I don't like this. Well, I mean, it's not like we'd have. I'd like to just read these directly and have other things be on an X bus. Well, I also don't like, so part of the problem here is that we have to move the data register to the accumulator and back. So maybe here what I should be doing, test of equal, I'm not actually doing anything here with the accumulator. So maybe instead of moving this to, well, okay, there's the back. Move P0 to data. I suppose I could do that. No, because the data register is holding the bullets. Right. And to do any math, right? To do any math, we have to be in the accumulator, right? But we can't be in the accumulator if we're reading. I just want to think about a smaller module here. So suppose this is a module that only kept the rounds in the accumulator, right? Then we could have a system where whenever we fire, like something else is doing the checking. All this does is test equal P0. This is the we are firing to 100. And whenever that's the case, we decrement sub 1. And then we test equal P1 to 100. And this means we're reloading. And whenever this is the case, we set to X1. Move X1 to ACK. And since that's used for firing, or hold up. X1's the fire. So P0 is our fire, right? So in that case, we subtract 1. Yeah, that's all we do. We subtract 1. No, that's our trigger. This is, we have decided that it is okay to fire. So I think on every cycle, we need to be outputting move ACK to X1. So this always tracks our bullet state. And whether we're triggering or reloading affects that. P0, P1. But that trigger is validated first. And it's validated by reading. Let's move back to X1. So this needs to be red just wants it to start then. So we move act to x1. That's the value to start. Then this goes into another chip, which checks if we're alive and have enough. Yeah. Not completely sure about that. But it's good to at least think about that, yeah. Move x1 to that could actually be x0. Move the ammo count to act when we are reloading. And this P0 is basically an AND of trigger and alive. Whereas P1 is just the reload. Well, maybe what I really want is just that on this chip. If I could make it. So part of the issue here, we're handling trigger. So this digit 0 is the reload. And this one here is the trigger. And the reason I'm doing this is because I kind of like having it in the X1. So if we can separate, or I like having it in the ACK, just live permanently in the ACK. So if we can separate this digit thing here into a different chip, then we could use two chips in tandem. The only bit of logic this is missing is the alive. Oh, ACK flashbacks. You know, it could have been more traumatizing, I suppose. We are getting tricky. That's good. That's why I didn't expect it to like come swinging out the gate today, though. I thought we were still in like tutorial mode. 5x. I don't think. See, our registers are limited to 999. I don't think we can even calculate like Act 2x. Let's see. 4-1 is like 65,000 or something. 3-1 is probably already too big. Let's not think about that. Okay, if we were doing it this way, we would need to wire it differently. So what I'm going to do, I'm just going to back out of here, make a duplicate, and just see if that's viable. Because I am kind of liking that. So here we have X1. What is this? This is a trigger. So this is trigger. And this here is reload. Let's just get rid of these. Let's move this chip out of the way. Trigger and reload, and X0 is the clock. I should probably make, nah, here, X0 is the clock. And then we need a bridge here. Okay. So now then we have another chip. This is the same price as a 5 plus that triple. So like if the logic's easier, then I would go for this. Okay, so now here we check if we are alive. And you're connected. This can be the thing that decides if we are firing, right? And then this thing just tracks our bullets. Does that work? I feel like this needs more information. So the point of this chip is oh, hold up. Trigger here isn't always happening. Trigger actually here means shoot. So if this thing is deciding if we are shooting, and then setting it over X1. So then first we need to trigger on and alive. And then we check the value from X0 and X0 greater than 1 or greater than or equal to 0. So this just does that check. And if we are shooting, then we need to send a value here to shoot. Shoot goes out. Shoot out to this thing here. We don't have enough pins for that. Oh, but you know what we could do? We could do something nice here. I think, maybe. So we can turn 3 basic inputs into an X output and put all the conditionals together. Right, so we have something that we can have something similar to this, but all it does is track our shooting state track non-empty. So non-empty, it is alive, and we have a trigger on. Before I commit to that, it's just yeah, shoot needs to go out to this fire. Oh, I mean, it can go out on the same input actually. P0 and P1. Okay, we're not gonna do this just yet. But you know, I do like that idea. I'll hold it for later. In order to make this here work, I think we kind of need to change what these two things mean. No, trigger needs to go down here. Yeesh. I need space. Okay, so trigger. Fire needs to go up here. Oh, right. Trigger doesn't go up there at all. Because what's going up here is reload and shoot. So this P1, will we even use an X0? I'm going to leave space for the X0 in case we want to use it. Okay, but this P1 needs to be forked. P0 needs to be the shoot. It can stay the shoot. P1 remains the reload. We can ignore this for now. X1, I don't believe we're using. Okay. P0 is the shoot. P1 is the reload. Okay. And then how do we know what we're shooting? Well, we have this X0, which is going to come from here, I suppose. Okay, so our first check, we have enough bullets. So we move X0 to AC. And then if we are dead, we turn that into 0. So we just gonna move P0 to AC. All we care about is whether AC is 1 or 0, right? Because that says we're firing. Oh, you know what? It's gonna fire prematurely, isn't it? We need to check all of them. Well, no, it's not gonna fire prematurely, not unless we send a fire signal out. Okay, so test greater than 0. Oh, we didn't need to move anything to ACK, so let's test greater than 0, ACK 0. There we go. Oh, test greater than. Okay, if that's the case, then we move 100 to ACK. 100 to ACK. Or like equivalently, we could just move. Let's start with alive. So we're gonna move alive. So P0 to ACK. And then if that's true, then we're gonna move reload, or we're gonna move trigger to ACK. And trigger is gonna be P1. Wait, what's P1? P1 is shoot. Right, I forgot trigger's not connected to anything right now. We could turn that into an X1. Okay, like, fine. Like we at least get something that works. It's not going to be cheap, but it's going to work. Okay, so now we move X1 to ACK. But only if we are greater than good. Test equal ACK to 100. And if we are still 100, then we can move the number of bullets to ACK. Move X0 to ACK. And now, if it is still 100, we can fire. So ACK 100, move 100 to P1. Okay. I need to change this output here. And yeah, that's the thing that, oh, hey, somehow we're not using this ammo. Reload. In the case of, oh, we're using X0 twice for two different things. Move back to X0, that's our output. Here it needs to be move X1 to ACK. Oh, gross. We can't flip this around, can we? All right, well, either way, we need more room. Hold up. X0 to ACK means that we are reloading. I should actually put that test here, reload. Okay, well, let's see which way it connects best. Do I have to do that? That. And now this P1 still wants to go up there, doesn't it? No, this is from here. So this P1 wants to go, oh, this P wants to go there. Okay. So X0 then is not output. X1 is our output. And then X0 is our... Oh no, X1 is still our output. Wait, why are we outputting? We are outputting if we actually fired. No. Move X to X1. No, we're not outputting anything. Oh, that's bad. If this chip's not outputting anything, then what good is it? Oh, we do. We always output the bullets remaining. Cool. And we're not sleeping. Part not sleeping blocked on right. So move X to X1. This one here. Oh, this here I guess shouldn't be conditional. I suppose we could make it our first one. So move X1 to ACK. And then this just checks if ACK is still 0. And if it's 0, we don't bother doing the other things. So basically, unless we are 0, if we're not 0, then we can do other things like move E0 to ACK, checking if we're alive. And I suppose I should use similar logic here. So one sec, my monitor is resetting. Okay. So we check if we're alive, we check if we are pulling the trigger. Or like, yeah, after we check P0, what's P0? So this is a rounds. We test that 0. If it's 0, there's no point in continuing. And then we move alive. So this is alive. And we check if it's 0. And if it's not 0, then we can move X0 to ACK. X0 being, did we shoot? No. X1 here is a trigger. Okay, X0 is the rounds. Move X0 to, this is trigger. So we have rounds, we are live, we are pulling the trigger. And after all of that, if our ACK is 100, let's just make that similar to the others. So as long as our accumulator is not 0, we can fire and then sleep. Cool. Heart not sleeping, blocked on read. Oh, let's move X0, the trigger. Wait, blocked on read. Why is it not able to read from x0? x0 is x1 from here. Oh, we used x0 twice, that's why. x1's a trigger. There we go. Okay, our fire is not resetting to 0. So at the start of all of this, we should reset that to 0. Move 0 into AC. Nope. Still not quite there. Well, at least the hit and respawn bit here is working fine. In fact, like, yeah. That could probably be. I wonder if this couldn't be 1 to 3 chip. We can refactor that later. Our issue here, when we run this, after we fire stays on, even though the trigger went down. So the trigger is dead. Right here, the trigger value is 0. We move x1. Oh. Right, we're not bothering moving x1 down. Well, let's go to that spot. Okay, so what's going on here? So fire is still 100. AC is now to 0. Oh, we should always move. When do we move AC to P0? 100 to. No, what we should be doing. We don't need to do another test here. We should just always move AC to 0, to P1. Move AC to P1. Always, at the end of every cycle, move back to P1. Which means we don't need this test equal. Yeah. But if AC is positive, it needs to be. You might get a value that's too low sometimes. Let's see. No, because the live at least makes that work. Okay, we've got something working. And it's pretty, it's at least understandable. Expensive power usage. It's expensive all across the board. Oh man. I want to go back to this to trying to use. Like this was very close. It just needed a little bit more room. Thank you. Right, like this would certainly be a lot cheaper. Maybe. So P0. Maybe I move that live up here. Where are we using P0? P0 to AC. Alive, P2, and Let me just go back here. I still like the idea of putting 3 P1s into here, and all we have to check is that if this is 111. Right? We have a three-way conditional here. So we wouldn't be using this reload. This P0 doesn't need to be directly connected. So we could have a chip like this. Oh boy. Yeah, we don't have enough room. Let's move this up. We need to move up even more. What we could do is move this to the right and loop it back. I don't know if that buys us much. Well, I suppose we could loop. We could do something like this. P1, and we have a bridge over here. Oh, we can't bridge over that. We could just move this up, I suppose. And in any case, I think this needs to have the reload. Just clear out our wires a little bit. Okay. So reload. We have our fire. Now trigger, enough rounds and alive can all go here. We do need ammo. Suppose if we're doing this, we can just tighten that up like so. Okay, this controls the fire output. Okay, so trigger connects here. And the last thing that connects here, fire, alive, and enough bullets. Where's enough bullets coming from? Oh, hold up. This thing connects both ways? Does it connect both ways? It does connect both ways this whole time. Okay, that's nice. So I could do something like put it on the right side here. Ammo. There we go. That clears us up some room. We do need, though, we need a shoot control. This here just means, hey, we have enough bullets. And no matter what, it needs to have a P0 connected out here. Do we need another chip, don't we? Yeah, if this is gonna work, we need to be connected to another chip that's telling us if we're firing and we have enough bullets. Or like we can just convert an X1 into a P. But if we're doing that, we might as well. So trigger pulled, we are alive, and this means we have enough bullets. So this is our thing then that stores bullets. But I think the circuitry is fine here, right? Like, what's the cost of this gonna be? Maybe be nice to have more room here on the right. Or like put this ammo, attach this ammo directly here. Okay, so what does this expect as input? I suppose geez, is the input here just going to be circular? We could do that. Input. Yeah, so we read from there. No, we need the number of bullets. That's what it's reading from here. This thing is actually not keeping track of the number of bullets at all. That has to be here, because it's the one that is connected to the ammo for when we do reload, and it's connected to the reload. So what this module does for the most part is it notices reloads. Reloads work whether you're dead or alive. And it sends that number here. Sends the number of bullets. So it looks at if we are firing. No, it's the one that decides that we're firing. And it decides it based on this. So you've got a loop here. We kind of have to decide where this all starts. I don't think we can just read X1 off of the bat, or X0 off of the bat, this triple. Unless like we're keeping track of the state from the last time. No, we need to do... Let's start with the reload. So let's test if equal P1. And yeah, this sends a reload signal over to the left. P1 to 100. If that's the case, we move 100 to X1. Right, and with that information, it can tell us, well, hold on. It doesn't really matter. Yeah, we'll just always tell the left module if we are reloading. So instead we'll write move P1 to X1. And the first thing this has to do is read off that X1. Move X1, well, let's test equal X1 to 100. And if that's the case, we move. Oh, no. I think if we're just gonna move bullets over there, however much we're reloading. We're gonna move over to this bit. So instead we'll do test equal P1, we're checking if we are reloading. If we are reloading, we're gonna move ammo, which is X3. Yeah. Move X3 over to X1. Otherwise, we move 0 over to X1. So this is the number of bullets we're adding. So the first thing we ever do is you don't just add 5 because we always reload to the maximum. So we're just going to check if it's non-zero. Test equal X1 to 0. Okay, so if it's 0, nothing happens. But if it's not 0, then we move X1 to hack. And this thing is keeping track of our number of bullets. No, I think this thing on the right should be keeping track of our number of bullets. And then if we fire... Yeah, because this thing doesn't know if we're firing or not. We know if we're firing here. This is the we are shooting line. Okay, so we are tracking bullets over here. So P1 is 100, then we're going to move the number of bullets, so X3, to data. And then we move data every turn. We move data to X1. Great. So now test equal. So we check that data, and if it is not 0, check if X1 is 0. So if it's not 0, we move 100 onto P1. Otherwise, we move 0 onto P1. So this is the whole not enough bullets conditional going here. Okay, so after we've done that, we can read this X0 value. And if it is equal to 111, so test equal X0 to 111, then we can subtract oh, hold up. Accumulator. I think accumulator should store. Accumulator needs to store the value. So move X3 over to accumulator. We sub 1. We sub 1, and we also say we are firing. So move 100 to P0. Yeah. Otherwise, we move 0 to P0. And I think that is it. Okay. Is that really all? There we go. This logic is so much cleaner. Oh, what's going on here? With x0, this x0 is now x1. Hey, okay, wait. It's not quite working. So fire is never firing. Even though in a condition like this, we are alive. Hold on, let's reset to one of the spots. So the first fire is coming up here. All right, so, whoops. We'll just step slowly into it. Right, we're moving data over. Oh, right, it's accumulator now. Accumulator just tracks the number of bullets. Okay. There it is, right there. Cool. I think this is a lot more streamlined. This makes me feel happier about the problem. Okay. Well, let's look at email and compare that. Oh, Joe, it would be great if you focus on business instead of constantly suggesting distractions. Also, I would destroy you. Just got word from my friends. He's purchased the building for his first. I can't bring myself to write it out. His first location. I'm not sure I want to imagine how much of his retirement he's put into it. Oh, geez. It's always nice to have a dream, but sometimes there's a reason you shouldn't pursue it, you know? And Joe really likes the Awesomeplex. Okay, that was cheaper. It took more power. It's marginally cheaper. Oh, wait, no. This one here? Oh, it's actually more expensive than the other thing we were doing. But we can probably use $3 ships. Can this fit on an MC4000? Yeah, it can. So there's that. So now this is X0. Where was my X0? Oh, hold up. We need AC and data. Data is keeping track of if you're alive or not. Okay. Maybe not. But also, maybe instead of storing it in data, like we can just put it in this here, right? And we just look at the third bit, the third digit. And this one, it's going to be hard to shrink this just because we need so many pins. Okay, I'll use a bathroom and be right back. Probably I'm not going to do another problem, but I might chew on this one a little bit more. Alrighty. Um, Geez, how do you simplify this? I think most of the simplification here would come at the circuit level. Well, I think this solution is pretty simple. Right, like the code isn't doing much. It's just not as compact as it could be. This here, it'd be nice if we could get rid of this chip. All this is checking is that we have enough ammo. So this is our have enough ammo chip. But I like it because it makes this thing here just a check if we are 111, right? Then we're not doing digit, digit, digit all the time. I still haven't quite figured out how to do ands. But I suspect you can chain these tests with like plus or something. I'll have to think about that. So this one here, it's checking hit and respawn separately. It's storing the data to and. I suppose we don't need to. Let's disconnect this. We don't need to check the individual digits. Right, what we could do, I'm gonna write it in this new chip here. So instead of moving x1 to ACK, we can compare. So test if equal x1. Let's see. The hit case is just a. Well, regardless, let's start from scratch here. So test if equal x0. And the case where we are just, let's do respawning first. So this is 10. And now if that is the case, then we move 100 to ACK. And then we test if equal x0 is just 1. That's the hit case. Move 0 to ACK, and then we sleep 1. Oh wow, I complicated that a lot here. Well, cool. And then every round we move ACK to P0. So we don't need this chip. Let's get rid of that. Okay, so already we're cheaper. There we go. Now these two chips. Can these two chips be one chip? This has an X and a P. This has an X and a P. It feels possible. The wiring would be a little bit wonky. So I suppose this P can connect out here, and this X would connect there. Oh, that wouldn't be too bad actually, the wiring. And we fit 3 more instructions here. 1, 2, 3. Before we ever sleep. We can totally do that. Cool. I would like to try that. Well, this P1 still needs to like wrap around. Right, like that all needs to be connected. And then that next one needs to be connected there, basically. But like if you put this here, that would do it. I think we would need to change our pins. We need to move this up. Do we need to move that up? This X1 moves here. The other X needs to be connected to the left. We just need to tighten this up here. And we can use a bridge. Okay. The wiring is a little bit wonky, but that should just do it. There, we just dropped a $5 chip. We got rid of a $5 chip altogether. And now this chip is multi-purpose, so we should be saving power too. Yeah. So we dropped to 10. And we dropped to 687 power usage. I wish I hadn't overwritten that. I'd like to compare before and after. So much more satisfying though. Now, what is X1 here doing again? It is bullet count. Rounds. I don't know if I can imagine actually a nicer way to wire this. This is actually nice. I like it. Well, what if we move that up there? We could do a double bridge, like so. I don't know if that's more readable though. I think that's a bit more readable. Oh, if only we could drop this too. I don't really think we can though, because we do need those 3 X inputs. If we could drop just one of these X inputs, like this here. Yeah, this is pretty satisfying. Oh, if I'm doing this, I need to change my values. P1 and P2. I need to add a 0 on each of these. There we go. Okay, I'll say I'm happy with that. We are firmly average for, or like peak for price lines of code. It seems like probably a common design. Power usage. We could profile it. Let's run the profiler. We hold R. Move Act to X1, test. Okay, these are running every time. Can we drop some of these commands? We are doing this almost every time. Move 0 to P0. Say we're not firing. Must we do that? Yeah, as soon as we're not. We just don't need to do it as often, do we? So the trigger comes in. No, reload comes in here. Trigger's getting into here basically through X0. So X0. And we either set to 100 or 0. We do kind of need to react to the trigger every time, so we do need to send a fire on every tick. So that's fair. And we send it either on this or that, right? So we're sending a fire. Sub 1, we're only doing that exactly when we're pulling the trigger. That makes sense. Move X3 to act. What's our X3? Oh, our clock. Right, when we reload. That takes as much energy as we are reloading. And here is our respawn, not taking much energy. Okay, I don't know if I can cut the power out of there. Cool Dad. Oh, okay, I've heard Cool Dad is a thing. I think we at least have to see what this is. Hope you all are sitting down right now because this one is going to be big. How big, you ask? Well, you might just be talking to the guy who negotiated the deal to make all of the light up color changing vapes that Cool Dad is going to give away on his this year's global tour. Dang, am I right? This is a huge deal for us. Literally millions of these are going to be given away. Looks rather straightforward. We get color vapes. We get color vapes in. Then we control some LEDs to get the shades we want. I put a bunch of extra LEDs in the prototyping bin too, since those should be fun to play with. Little tip for you. See a little triangle at the beginning of the XBus data packet? That's when all of those values in that packet are coming in. It's not like one per time yet. Yeah. Oh. Shame that Cool Dad's actual music, if I can even call it that, sounds like 2008 era dubstep across the parliamentary debate. If Parliament were populated entirely by across the parliamentary debate, if Parliament were populated entirely by screaming macaws, I have no idea why he's famous. My girlfriend Shomie is a fan. Some of it is quite danceable. Let's take a look. Vape pen. Red, green, and blue are simple outputs connected to an ultra bright RGB tricolor LED from top to bottom. When a data packet is received over the radio, pulse the LED as specified, red, green, blue, If a data packet is received while a pulse is in progress, interrupt that pulse. So the data packet is going to be multiple values, red, green, blue, and pulse duration. Interesting. So we start with this color, and those values go up, and this starts going forever. And then we interrupt. Yeah, that goes until it's interrupted. And this one here, we run for 4 seconds, and we stop doing that. You know, this might be speed enough to run. We do need 3 outputs. And each of those outputs, though, aren't just on-off. They all have intensity. Yeesh. So, we need a lot of chips for that. Well, hold on. Is it these 3? R, G, and B? Let's just try something. Move 50 to P1, sleep 1. Okay, so here red is constantly up there. Oh, and we can see it. We can see it glowing red. Let's make some animation. So, well, right. We can't use the DX300 here because that only outputs constant values like 100 or not. So we need at least 2 chips. How might we wire this? Okay. And we could just basically send the same input to both of these. Although I don't know if you can have... oh, let's use an X. Okay, so we receive on our X bus. Can we do that? Like we can read from both of those? Let's just try a thing. So move 100 to X1. Sleep 1. Move X0 to sleep 1. Okay, so can you read the same input twice, basically? And we'll just move back to P1. Yeah. Part blocked, part not sleeping. Okay, so we would have to move it twice. It becomes a race between those two, which is fine. Oh, well, we have to send 3 values actually. So this one will only need the 1 value. So 3 different values. Okay, so we're gonna keep moving X0 to accumulator. And that is the start. We jump back to the start if we're -999. And we have to keep track of time. Something needs to be keeping track of duration. It could be either of these. It needs to be something that's not this, right? Yeah, we could take turns reading here between these two. Can we be nice and do that? Like we have this sleep first? No, we'll have a race condition. We can't do that. I'm just wondering if we can do this in fewer than 3 chips, if we just use 2 chips. Because we have 1 X input. That does RGB and then that value. Okay, so this is the start in any case. And test equal ACK. Yeah, we can only read that once. So we test if the accumulator is -999. And in that case, we jump back to start. Otherwise, now we move accumulator. This is the R value. So we move down to X1. Then we move X0 onto X1. We move X0 onto X1. And then, geez, we need to sleep. We sleep 1 at the end. But before we do that, we need to move the time value somewhere. Also onto X1. Okay. We could say that it's down here. But now it would have to send a signal over XBus to this chip. I think we just need a bigger chip here so we can decrement on every clock. Yeah, the accumulator can store a time value, and this we can cache into the P1 instead, or into the data. That's the simplest way to do this, so we'll do it the simplest way. Jump start. This actually goes to data instead. And instead of X1, we are now using X, oh yeah, instead of X0, we're using X1. And now our output should change. Oh, why don't we make it X3? This third one, we need to send a time to both of them. So I'm going to... Oh, are we running into an issue here? I think we might be running into an issue in that... How do we control where these go? We need separate X buses. We can't send them on the same input because they might be read in the wrong order to the wrong thing. So we have an x3 and we have an x0. So red gets sent to the top one, x3. Green gets sent in there too. Blue gets sent to the second one. Oh, actually, this is red. Let's comment that red. Green. And this is blue, which means we need to go to x2. And then the time, I think the time can just be sent to both. So we'll move x1 to data, data to x3, move data to x2. Yeah. Time will call it duration instead. DUR. Okay. So I think that's doing its job. And we can just move x0 directly to P1, right? Yeah. Move x0 to P1. Move x0 to P0. Move x0 to accumulator. Yeah, the duration. Then on every tick, we decrement that by 1. So sub 1. And then sleep. Sleep 1. And then we need to test if our time is set to 0. So test accumulator is equal to 0. Then we need to move zeros into here. Move 0 P1 and move 0 to P2. P0 and P1 rather. Okay. And we can do some very similar logic here, except we just delete some lines. We're not using P0. All right, we might have an issue with when we're doing the sleep, but we'll see what happens. Oh, that part is not sleeping. We'll just throw in a sleep here. Sleep and then jump. Part not sleeping, but blocked on read. Right, because this decided to sleep. Yes. Oh, geez, it's the same thing from earlier. All of these -999s need to be sent along. I should be sleeping anyway. It is past my bedtime. We can leave that hanging. They all need to start with this logic here, which is a little bit annoying. They all kind of need to sleep in sync. Isn't there a sleep until input command? Yes, there is. there's this SLX, so that sleep until data is available on the X bus bin specified by the operand. Okay. So we can sleep and then read. SLX. SLX on X0. We should put that at the start, rather. SLX X0. Ah, that could have saved me earlier. SLX X0. So next time we can do that refactor. Oh. Does that data get lost? Hold up. Okay, so data got sent to all of those. Oh, this sleeps twice. Okay, so the first time around, the two small chips are just waiting. And the big chip runs in a loop over at -999. Wait, did we actually get a value? Right. Move X1 to ACK. This is actually moved to data. There we go. Now that's doing the right thing. That was our. That was part of our bug. Well, it's doing something. Okay, so first time through, it's -999. Now we're sending data over. So we send G. No, that's actually R. Okay, so we send R across, which is a 0. Now this one has stopped sleeping, so it sends the 0 over to P1. And now it's blocked waiting for the G value, which actually has just been sent. 50. Okay, great. And now we have 100 being sent to blue. That looks good. And then we move data X3. We'll write the clock values. And then we immediately decrement them, which I'm not sure is correct. Oh, the decrementing doesn't work because it depends on how long you've been sleeping. So we should be adding I suppose what we could do is track pulse length here. And then we just send 0 over to all 3. Yeah, sleep was part of the reason I hesitated on that one. Move X1 to data. And on each iteration, we do need to, so let's move this to our ACK, our accumulator. Duration to the, and every time we sleep at all, what I should do is just wrap all of this in a big conditional. So we're going to do a test not equal T&E. What is the actual test? Yeah, I suppose we could just do test equal TQ. And we only do all of this if that is minus. And one thing we'll always do is subtract the accumulator. And if the accumulator, so we subtract 1. Then if the accumulator ever hits 0, then we send 0 values over for all 3 of those. We don't have that many lines of code though. Right, we don't need to be sending that over anymore. The duration. So these actually become simpler here. So we don't need this, we don't need all of this logic at all. Okay, so these chips are pretty dumb. They just wait for input, and yeah, they do what they're told. Is this harder or easier than real programming? It's different. It's different even from TIS 100. So I finished TIS 100 in the last week. This is, so you're really constrained, right? And that's where the puzzles show up. And what I found generally is like the logic isn't what's difficult. What's difficult is like fitting things into chips. And then this has the added layer of like the wiring. It's the space chem problem? You mean like it's different in the way space chem is? So we move RGB values over, right? And we set the duration. We're always going to sub 1 and sleep at the end. But now we're going to test our accumulator. So test greater than. So test that our accumulator is greater than 0. Or do you have a test less than or equal? Greater than 0. We're just gonna make this negative. So if it's not greater than 0, we need to send 0 values everywhere. Move x1 to move 0 to x3. The gameplay is about constrained space. Yeah. I think that's less true with this game than it is with TIS 100. There you're really constrained. Like a problem I solved in the last day was reversing a list, and reversing a list without using any data structures. And what made it difficult is you could barely fit an iteration onto a single node. So like that was a golfing challenge, and then like a layout challenge because you only have so much space. So we can move 0 to all three of these. Move 0, x3, and then move 0 to x2. Okay. Beautiful. Oh, that's lovely. Nice. Okay. We're not going to return to the email quite yet because I think there are obvious things to fix here. For one, we could just use our P outputs directly. Right, so instead of using x2, we can use p0. So there's p0. And we can do similarly for this. I am behind the curve in those graphs. You know, after I finished last time, I spent some time optimizing, and I got a lot of them down really low. Like I optimized for cost, for power usage, and for lines of code. Okay, that's a little bit better. And I came in tonight feeling pretty confident until I ran into the last problem. And I hadn't tested my brain enough on making a circuitry. Okay, so we can connect P1 directly. And what we could use instead of this, oh no, I was thinking we could use a D3 to convert that. We still need a third pin. So here we go. Sleep until we have X input, move X to P. Oh, what did I do? Oh, right. R is now going to P1. So R goes to P1. R goes to P1. R, G, B. Okay. There we go. That's a bit nicer. Okay. Someone did it cheaper. Did they do it in... I'm not sure what they did it in. Why is my production cost 8? And I guess I am using a lot of power. I suppose my production cost is 8 because of this chip, which is necessary. I think someone probably managed to do this using these two, using a smaller chip here. I would kind of like to end. We probably don't need to be sending so many zeros here, right? Like, let's pause this and look at our profiler. Well, we start sending constant zeros, basically, once the duration runs out. So here, we send zeros twice. We basically need to send the zeros once and wait until we have more input. Yeah, I think basically we shouldn't test this all the time. We should only test it when it turns out we had a positive value. I think the rising edge detector example here in the manual, I think it has something for this. Right here, what's going on? We check if we're equals 0. And then we check if P0 is 100. Wait, what is the accumulator? So basically, if accumulator is non-zero, then we check this. If accumulator is 0, we don't do either of these checks. So this is like a second chance to fail this, right? And basically move 1 means that both of those things were true. That had to be true. That had to be true. This second line here is going to happen if either of those first ones failed. If that fails, or if that fails. So this runs only when it's both true. That is an AND. Is that an AND? Am I seeing that right? If both of those, if one or the other fails, is yeah. So if not AND, okay. Maybe that does not help here. We only need to check, we only need to send these when we are in this larger loop. Yeah, I suppose we put this here. No, I don't think that will work. Because then how does it ever turn off? So this is the only time we have input, right? And after that, we might get a -99. But we're going to get a bunch of -999s. And during each of those, we need to be, you know, that minus is probably fine. No, it's not fine. So it fails here, right? Because it's still minus. We are never getting to this line of code. So what this needs to be then, that always runs, and then we have a second conditional. That basically we haven't sent 0. We don't really have another register of that. I suppose we could save it to the data register. We should only ever run that test in the first place if it's not already off. Like, do you run the test on itself? That is gnarly. Wow. And our profiler, oh, our profiler is worse. Oh, you know what? That's silly. We only need to set it once, right? We set it once to 0 and we latch it. Okay. It's too early. Too early in the morning. That will have to do. That'll have to do. I can always optimize it later. I mean, overall, not bad. Greetings all. With every project we take, there are factors we can control and factors we cannot control. We could not control the fact that Cool Dad was arrested and jailed for possession of amphetamines as he attempted to enter Japan, thus canceling the world tour. However, there was something under our control, and that was the terms of the deal. We could have negotiated a better contract that would have allowed us some recourse if something like this happened. Instead of leaving us on the hook with 100,000 useless color-changing light-up vapes for us to dump at the basement price just to get rid of them. Uh, that's a very nice way to say shoulda, woulda, coulda. A very polite way to be upset. Alrighty. Apparently, Cool Dad is like a recurring theme of some sort in Shenzhen or across Zachtronics games. All right, let's find. Let's find someone to raid. Or actually, here. Let's see. I'll probably still be working on this next week. There was that game project. I think I'll keep holding off on that, the prototyping no ideas, until I learn how more of these things work. Um, and at some point, I actually would like to share some TS100 stuff because it's really cool. Like, I don't know, maybe I'll just do a playthrough of. I know them pretty well. I could just do like a playthrough of the first 24, first 25 puzzles. I bet I could do the whole thing in 3 hours. Um, but yeah, until next week. Yeah, speed run. I was thinking less of a speed run because what I want to do is like a live walkthrough. So I could like edit this into a tutorial and not just a playthrough because if you if you just play, I want to share my thought process as it's going to the point where like if you're watching this, you can be like, okay, well, I see where this is going. I can pause and take it from there. So I want to share like how I would reason through those problems. Yeah, speed running it is kind of weird, but like a blind playthrough, I think it's cool to see someone struggle. Um, but it'd be nice to have just a clean. Here's a thought process, and these are the ideas that are motivating me to do the next thing. Yeah, truly. Yeah, you just memorize and then then it's a speed typing test. It wouldn't really work as a speed run. Um, hmm, software Twitch. Have I seen speedruns The Witness? I have not seen anything about The Witness because as a game I'd love to play and I want to play it completely blind. So I know enough about The Witness to know that I would like to play it, and that's it. Um, and I think when I play it, I might stream that too. That might be fun. What we need is a roguelike coding game where each puzzle is randomized, random perks and features unlocked along the way. Yeah. Yeah, we need to hop on this roguelike trend. hmm I actually just saw my younger brother just started streaming The Witness, and he was texting me saying that I should play it and do it for the stream. So he's playing that. I'm not gonna watch him because I don't want to spoil myself on it. But he's saying I'll enjoy it a lot, so I trust him there. Howling Fan Todd's is up. We could hang out with him until 5 a.m. 6. That guy stays up late. um, yeah, I'll probably raid him. By the way, Liquid Cake, have you uh have you planned to stream Cinecore yet? Because I definitely like to see you do that. You can still get satisfaction from solving them even That's fair. Um, yeah, I feel that way about these games here because it is open ended. So with these electronic games, it's still like even if you know how to solve it or know a solution, like you can still do like a different solution. And like working your brain through it is just kind of feels good. Snakora is in your plans. You'd like to give it a go, but you've got a few coding things you'd like to get through in the near term. That's fair enough. Eventually, whenever you do it, I'll be there. I'll want to see it. Zach definitely knows how to make a coding game. Maybe now that Eric Wassel has more time, maybe he'll do a coding game. Also have two AOC. I'm not satisfied with Day 10 Part 2 either. That's one I want to revisit. I also have in my tabs here the puzzle you wrote. I'd like to do that. Maybe one of these Monday nights, that's what I'll do is solve your puzzle. Maybe I'll just wait for you to show up and be like, okay, Liquid Cake, we're solving your puzzle. Um, I feel like I had something more to share about problem is that when you go to bed, is when you wake up. When do you wake up? So like it's 8 a.m. here. Oh, well, clearly I'm not in bed yet. um, I can do like a 2 a.m. I can do a 2 a.m. Right, you're in the UK. I mean, I'm often up this late. If I can solve in an hour from 2 a.m. to 3 a.m., then maybe that's pretty reasonable. I'm reserving Monday as like my one day to be up late in the week, and then the rest of the week I have to go to bed on time so I don't hurt myself. All right, let's do. Oh, whoops, my rate disappeared. Oh, did it already go? Oh, all right. Well, have a good night. Wait, wait, are we still? I don't know if we're still live. We're still. Okay, let's end the stream here.